Now that we know about the squeeze theorem, let's use it. Let's use the squeeze theorem to evaluate a limit where x is approaching 0 for the function sine x. In order to do this, we need to find that inequality where we have a small function, a large function, and then our function squeezed in the middle. To do that, we're going to first look at the unit circle. Any point on this unit circle can be described as an ordered pair of cosine of the angle it takes to get there, sine of the angle it takes to get there. The angle is imagined as a ray that's rotating through the circle. So for some angle theta, we could imagine that the ray, which started on the x-axis, rotated counterclockwise, and it intersects the circle at some point, and that point can be described as cosine theta for the x-coordinate, sine theta for the y-coordinate. Now that means sine theta is actually the vertical distance from the x-axis straight up to that point that we see on the unit circle. And to get to that same point, we could have traveled a different path. We could have walked along the edge of the circle, along the arc of the circle. That arc is described as theta. So angles can be described in two ways. You can describe a rotation, I turned around, for example, or you can describe a distance that you had to travel to match that same angle. So notice in our picture, theta looks like it's an arrow pointing to the ray. That's how much the ray had to rotate. But also, theta is that arc along the edge of our circle. We can tell that traveling along the arc is a further distance than traveling along this vertical orange arrow, which means we know that theta, the radian version of the angle, is always bigger than sine of theta, this direct distance traveling vertically to that point. And if we limit ourselves to only consider points in quadrant 1, then we can come up with this inequality. Our function sine theta is sandwiched between two other functions. The small function is 0. The larger function is theta. Once we have this inequality established, we can start using the squeeze theorem. Now, our function has a variable called x, and I described all of these relationships between 0, sine theta, and theta as functions of theta. But that's an easy fix. You just rename your variable. Now we're looking at 0 is always smaller than sine x, which is always smaller than or equal to x. To use the squeeze theorem, we first have to verify that our small function and our large function have limits that go to the same place. So, is it true that the limit of 0 is equal to the limit of x when x is allowed to approach 0? Yeah, it absolutely is, which means we can take the limit of all three terms of that inequality, and then we'll see that our limit, sine x when x is approaching 0, is squeezed between two equal values, which means we can conclude that the limit we're looking for is equal to 0. We just demonstrated using the squeeze theorem to evaluate a limit. Let's try another one. Let's evaluate the limit where x is approaching 0 for the function cosine x using the squeeze theorem. Psych, just kidding. We actually have shortcuts that will allow us to build on what we just did to find the value of this limit, completely bypassing the squeeze theorem. Recall that the Pythagorean identity tells us sine of an angle squared plus cosine of that same angle squared, it's equal to 1. So we can solve that expression for cosine x and see that it's written as a function of sine x. We know limit laws, so we can rewrite our limit that we're investigating using our limit laws and this expression of cosine that is equal to a function of sine. So we sneak the limit inside of the square root, we distribute it over the difference, and then we sneak the limit inside of the square on the sine x squared function. We know the limit as x approaches 0 of sine x is equal to 0, so we replace that limit with its value and simplify to find this limit is equal to 1. So now we have learned that the limit as x goes to 0 for cosine x is equal to 1, and we didn't even have to use the squeeze theorem to get there. Finally, we have everything we need to be able to evaluate the limit that we started investigating at the beginning of this video. The limit when x approaches 0 for the function sine x over x. We need to build that inequality involving our function, a smaller than function, and a larger than function. Returning to our visual of the unit circle, recall that sine theta is still smaller than the radian measure of theta, but we do need one more term here, and that's going to be tangent theta. Now, tangent theta is tangent to our circle at a point, and it points up to the same ray that our theta angle rotated for us. So in this visual, we can see that tangent theta is larger than the radian version of theta, which is larger than sine theta. That is the inequality that we're going to start with. Now you might observe that's not the right inequality because it doesn't have our function, sine x over x. It doesn't even have sine theta over theta. So it's not quite ready, but we're going to start with that and build up to the inequality we need. First thing we'll do is divide every term by sine theta, and then we'll simplify. Sine theta over sine theta is 1. Copy down our center function, theta over sine theta. And then notice that tangent theta over sine theta reduces. Tangent is sine over cosine, and we're essentially dividing that by sine, so the sines cancel out. We're left with 1 over cosine. So we built our inequality using that unit circle visual. Then we divided every term by sine theta, and now we're close, but we're still not exactly where we need to be. We have theta over sine theta, but we need that to flip over. So we flip our inequalities, and we flip all of our ratios. 1 flipped over is still 1. Theta over sine theta now becomes sine theta over theta, and 1 over cosine becomes cosine. Notice that all of our inequalities have reversed direction as well. You can always do this, flip the inequalities and reciprocate all of your terms. Now we have the inequality that we need to be able to use the squeeze theorem on this function sine x over x. Just for consistency, let's change all of our variables to be x, and then we'll check that the limits of our small function and our large function go to the same place. We know the limit of a constant is just that constant, so the limit as x approaches 0 of 1 is just 1. And just moments ago, we determined that the limit of cosine x when x goes to 0 is also equal to 1. So we know that we have satisfied the squeeze theorem's conditions. We found a smaller than function, a larger than function, and those two functions go to the same place when we allow x to approach 0. So our inequality then squeezes the limit that we're looking for between two equal values, which means the limit in the center of that inequality must match those equal values, the ones that it's being squeezed between. So the limit when x is approaching 0 of sine x over x, it's equal to 1. This is a fact that we will use throughout the course, so you're going to want to memorize this. You won't have to reproduce it necessarily, but you will need to know that once you've isolated that limit, sine x over x when x is going to 0, that you can simply replace it with a 1. There's one last limit I want to talk about before we wrap this up, and that's for the function 1 minus cosine theta all divided by theta, where we allow theta to approach 0. To evaluate this limit, we don't need the squeeze theorem, but we do need some of the results that we just learned using the squeeze theorem. First thing we're going to do is multiply the entire function, top and bottom, by the conjugate of our numerator. So we're going to take the terms in the numerator, copy them over, but just change the sign between them. So instead of 1 minus cosine theta, we have 1 plus cosine theta. That's being multiplied to the entire numerator and the entire denominator. Now our numerator has created a difference of squares, so we can rewrite that as 1 minus cosine squared theta. I'm going to leave the denominator factored for now. I don't see a point in expanding that out, so I won't do it yet. In the numerator, though, I notice that I'm using the Pythagorean identity. Sine squared plus cosine squared equals 1. It looks like I could make a replacement there. Instead of 1 minus cosine squared theta, we can call the numerator sine squared theta, since those two things are equal. Now I'm going to use the limit laws, where we notice that the limit of a product is a product of the limits. So factoring our function, splitting the sine squared in the numerator, and splitting the two factors in the denominator, we can evaluate each limit separately and then bring them back together as a product afterwards. One of our factors is sine theta over theta, and we just learned that the limit when theta goes to 0 for sine theta over theta, it's equal to 1. Sure, we did it with x as our variable, but that doesn't make a difference. It's still the same value. Next, we look at the other factor, sine theta over 1 plus cosine theta. That gives us a 0 on top and a 2 on bottom. 0 divided by 2 is not undefined, it's simply equal to 0. So the limit of this product is the product of 1 times 0, which is 0. Therefore, we know the limit when we take theta going to 0 for the function 1 minus cosine theta over theta is equal to 0. This is another one of those facts that we'll see pop up throughout the course, so this is one that you're going to want to memorize. You don't necessarily have to be able to reproduce it, but when you see the limit of a variable approaching 0 for 1 minus cosine of an angle divided by that same angle, you should be able to recognize that it'll be equal to 0.